We're here to study the mechanical properties of shale, and shale's gotten a lot of attention recently because of, well, hydraulic fracturing, so unconventional reservoirs. It can also be a seal rock for oil reservoirs, and it's also potentially important for places to sequester nuclear waste and CO2. And so the idea is we want to understand how these things behave under deformation. So if we're pumping fluids in and we raise the stress on the rock, is it going to crack? Is it going to allow things to escape that we don't want to? As it turns out, in shales, you have these clays which are very platy, so they all stack up like this. And what tends to happen is because they're very platy, when it breaks, they want to break this way. And so they have a preferred direction of breakage that's partly determined by the orientation of the clays. And we can use the X-rays to image how those orientations develop and how they develop under pressure, temperature, and stress. And so we can make some predictions about how the shale is going to fracture. And so the idea is if we know something about how these behave under pressure and temperature that we would see in a typical shale bed, then we can get an idea of how to effectively pump things down there without breaking the seal rock and having that material come back up or contaminate drinking water, contaminate the environment. We came to APS, and in particular the Jesse Cars beamline, because it's one of the few beamlines in the world that has a large volume press. It has 6 ambles and it compresses a very small cube size sample. So this one's about 16 millimeter edge on the cube. And what we do is we take that, there's a small shale sample inside, and there's 6 ambles, and we have 4 on the sides and 2 on top. And this allows us to squeeze everything together so we can generate a hydrostatic pressure. So our sample doesn't change shape, it just gets smaller. And then what we can do is we have a little heater in our sample assembly. We can heat it up to relevant temperatures to what we would expect in a typical shale deposit. And then we have the top 2 rams that are differential rams, and they can cycle in and out. So we can shorten or lengthen. We can actually go up to pressure and we can actually pull the sample in tension and watch it break. There's a gap here, a hole here that lets the X-rays through, and so we can bring our synchrotron X-rays through here, and then on the back side we have a series of detectors and imaging equipment to do both radiography, so the same way as if you break your wrist and you go to the doctor, so we can image the sample that way, and then we also have a detector where we can take X-ray diffraction measurements, which is how we measure the mineral orientations and the strain in the crystals. I hope that it'll at least provide some groundwork to doing safer hydraulic fracturing if that's where the energy industry is going to focus, so that we can do this. We can get better recovery in an environmentally responsible way that's safer, and also that we can do a better job if we're going to use this shale beds as targets for sequestration of nuclear waste or CO2 sequestration, that we know we can put it down there and it's not going to come right back up, or that it's not going to come out and contaminate the environment.